introducerende statistik, og vi har tonsvis af andre gode statistikkurser. Så I skal selvfølgelig ikke gå fra det her kursus og tro, I ved det hele, men I har fået en rigtig god bund i det her kursus, når I er færdige med det. For at kunne, og det er det, der er det store, kan man sige, bidrag fra statistikken, for at kunne kigge på data og analysere dem på den mest intelligente vis, der kan forekomme, så har man brug for lidt sandsynlighedsovervejelser og sandsynlighedsbetragtninger, fordi det, der gør os intelligente, når vi lærer af data, både i business og i science, det er at erkende, at det vi ser, kun er et muligt udfald af det, der kunne være sket. Så der er et sandsynlighedsaspekt i det, et tilfældighedsaspekt i at kigge på data på den rigtige måde. Og derfor skal vi lige lære en lille smule sandsynlighedsteori, sandsynlighedsregning, sandsynlighedstankegang, fordi det er det, der gør os gode til at kigge på data. Det er det, der gør os gode til at være statistikere. Det er, at vi kan anvende noget sandsynlighedsteori i den måde, vi kigger på data på. Så jeg prøver ikke på at lære jer at blive sandsynlighedsteoretikere i det her kursus, men jeg giver jer lige det minimale redskab inden for sandsynlighedsteorien for at kunne begynde at lave statistik. Man kan faktisk på ganske glimrende vis også lære mere sandsynlighedsregning. Der er masser af ingeniørdiscipliner, hvor det også er meget værdifuldt. Men så skal vi tage andre kurser end det her. Jeg har taget en lille historie med for at motivere på lidt fjollet vis, men det gør vi så nogle gange, at det her med de kontinuerlige fordelinger, for eksempel normalfordelingen, som vi skal bruge mest krudt på, mange har hørt om den før, den skal vi lære om. Der er en hånd oppe, spørgsmål. Oh, god damn it, fuck you and fuck me and thank you, sorry for that. I was like, why the heck are you interrupting my nice speech here? Okay, sorry about that. I gave a very good introduction there in Danish to all of you. Thank you for stopping me now and not in 45 minutes from now. I don't know what went on there. Very good start this morning. Speaking about that, yeah, you can see it in many ways. Let's go up. You are 50, and then it goes down again, right? That's the challenge here. You have to rely on other qualities when you get at this point. The normal distribution, a continuous one. I'm not going to repeat all the introductory words. Can be used as a model for a lot of real-life phenomena that we meet out there. And as such, it's a very important distribution for us when we are going to use the distributions to look at our data. For instance, it is used as a model for IQ scores. And that can be discussed in long terms, to which degree you like those and believe those to be good scores or not. We can take that discussion after 10 o'clock if you want. Anyway, if you want to, you could use it as a model to say that the average guy is 100 and then there is a certain variability, of course. Some of us are below and others are above, right? And with a certain standard deviation of 15 points, that's the model as it's used. You could start at least talking about different things. Let's just have a look and then we'll get back to it later. I like this one, so let's... Since we're at a elite university in Denmark, top ranges on many international lists, of course, we are not going to discuss what goes on below 100 here, right? So anyway, what is the definition? Hey, this is you guys, right? Pretty well. And then down later on, I'm part of the here. Oh, this is me, not remembering what language to use. Fantastic. Anyway. We'll get back to it. I have a little exercise later. We're going to think about, and I asked you in a little quiz so that you'll have the chance to look at. You can actually find it already now. I wonder how many high geniuses we might have in Denmark, according to this definition and this model. let's see if we can find out about that before we split in a couple of hours from now. So let's go to the topic, that is the continuous distributions, continuous. Feel free to still join in if you like. Don't worry about interrupting a little bit. I interrupted all of us anyway. Today's lecture very much is like the lecture from last time on the discrete probabilities. So it's built up in the same way. We're going to talk some abstract basic stuff in the beginning, then we go specific, we go back to the abstract, and we look at some examples. So, continuous variables. For instance, the IQ scores, or the amount of alcohol in your blood, or the amount of your PSA level, prostate-specific antigen that you measure on old guys to see if they have a problem. Any such thing, the height, the weight, anything quantitative that really is on an underlying continuous scale, right? When we are going to talk about probabilities on such scales, we have to think a little more carefully about how we define a probability function, or what we last time called the density function. Because last time we defined the density function like this, right? The density function is the function that collects all the probabilities of the system that we are modeling in the given context. Now I'm explicitly emphasizing that that's not how we can do it. And for the one reason that in the continuous world, a bit unfortunate with the sound there, but in the continuous world, this point probability of some specific event happening is actually 0. The probability that I'm exactly 170 centimeters tall is 0 if you want. Because there's an infinitely amount of possible values that I could have, right? It could be 170.000123590, and so the density function in the continuous world is still the function that somehow collects the probabilities. I say that in a sort of loose way, but it collects the information about probabilities, not by pointing at individual probabilities, but by, and that's actually where the density, where the name really comes from, by giving the intensity or the density of the probabilities such that areas under the density function becomes probabilities. That's the way we can have a abstract way of handling probability functions in the continuous world, that we have some function, a positive function, otherwise it doesn't make sense, and if it is a function which is standardized in a way such that the total area under the curve, that is the integral along all possible values, if that integrates to 1, this is then a meaningful model for probabilities, you could say, a meaningful collection of probabilities, in the sense that the values themselves are not probabilities, but area under the curve are probabilities. That's still, it's just in a way, it's just a functional version of the histogram if you want. If you measure something quantitative like the heights we did, make the histogram, you can sort of smooth in maybe a curve like that, and you have a density function. We also have a distribution function today. And in fact, this definition is no different from the discrete definition. This is the definition of the distribution function. Like last time, it's the probability of falling below the point. This is still the definition. However, today, in the continuous world, this definition then amounts to the integral. Let's see if I brought, not really, I can put it here. It's the integral. Here I have x. It's the area under the density up to the x value. Then in fact, we're not going to use that a lot in this little introductory course, but that is used a lot for the mathematical foundation of statistics, that it's then in a way, almost by definition, when the distribution function is the integral of the density function, then the density function is the derivative. The distribution function taking the derivative of the differentiated one, or how you want to say it in half Danish. So yes, actually stuff that you learn in math sometimes pops up in other areas and becomes important for your ability to be able to dig into other areas. I'm sure all of you know, but here's another example. If you want to go to become real stats guy, it's good to be able to find derivatives. Is that a question? Yeah. Please?
Can you just repeat the relationship between the two?
Once again?
Can you just repeat the relationship between the two?
I can repeat the relationship. It's here. You can find the density by finding the derivative of the distribution function. That comes from the definition of the distribution function being the integral of the density function. Here is a picture of a distribution function. This is a function that will always go from 0 and then in some continuous way go up to 1, because whenever you get high enough, the probability of being below 1 million will be 1, right? And probabilities between A and B can then be read off like this. Actually, although we didn't dwell on it for many seconds in the presentation, but it's still in the e-notes, we did already meet in the first chapter this little function, or called the ECDF, the empirical cumulative distribution function. We already met that actually. That this is a way to plot empirically it's kind of the accumulated histogram, if you want, although it might not be that clear, but basically you're plotting each observation, and then you plot, if I have 10 observations, I plot 1/10, 2/10, 3/10, 4/10. It's like plotting the quantiles, the observed quantiles actually. So in that way we can also visualize empirically by the inbuilt ECDF in R. We can show on real data this empirical version of the distribution function if we want for quantitative data. Then we also need a little more abstract stuff. On day 1 in the course, I told you how to compute a sample mean and a variance. The sample mean we have all met previously, many years back in elementary school. The variance probably many of us also met, maybe not in 3rd grade in elementary school, but then potentially in high school we met the variance the first time. And if not, then you met it in my course and I told you what it was and what it is. Then we saw last week that we could define what we think of as the mean, or sometimes we could also call it the expected value. That could also be a name for it. The expected value of the random variable x following the distribution given by the density function little f, if you want to put all those words to it. We can do that. Actually, I brought this. I should put that. We brought this, which is a comparison of last week, just to make the link, what I showed you last week. Now, I am actually doing the same thing as I did last week. Last week I told you, let's take the mean outcome by taking each possible outcome and then weighting with the probability that it occurs. Like if it was a dice throw, a fair dice, it was 1/6 of a 1, 1/6 of a 2, and so on. Altogether that would be 3.5. That would be the expected value of the throw with a fair dice. That is 3.5. We saw that last time. Now in a continuous system, I am defining it like this. I'm still integrating all possible outcomes with, if we want to be loose, with the same thing with the probabilities that things occur. But now we need to use not the probabilities, but the density function that is the probability intensity, you would say. And for those of you remembering a little bit about your math also, you know in a way that there is a close link between summations and integrations. A lot of the math theory about integration comes up by approximating the integration by a summation that you then let tend to infinitesimally more, small things that then finally converges to the integral. Anyway, we can define the expected value, the mean of a continuous probability system. And I think you also remembered last time that maybe that's not so interesting, but what is very interesting is that we can be able to know about the variability of systems. I think you've already got the feeling of knowing about variability of the random things that we're studying is a really, really important thing for us to be intelligent about the value of the information we have. If what we see comes with a very high variability, it's not of very high value to us. But if what we see comes with a very little variability, if what we see is very precise, if we can convince ourselves about that, then we should put high weight on that information. So the concept of variability is really at the heart of all this, what we're doing here. So, last time we defined the discrete system variability like this, taking each individual observation's difference to the mean, squaring it and meaning it, taking the mean with respect to the probability that they occur. And here we do the same thing but in a continuous world, right? Each potential outcome difference to the mean, square it, and then average with respect to the probabilities with which they occur. Probability density, to be exact again. Sometimes we would call this the variance of x, or even write var of x. If you want to think about it, actually you will see that this is the same as the mean of x minus the mean of x squared. Mathematically speaking, now I'm abstract, right? Don't worry, we're going to be specific in a second now. The definition of a mean or an expected value, mathematically speaking, that is an integral. So a mean is an integral, and the funny thing is that a variance is actually also a mean, but it's a mean of a different thing, right? The average is the expected squared deviation. So the variance is the average difference. So that's maybe a concept, maybe it's getting too weird now. But anyway, you don't have to worry about it if you think it's too weird. It was just to get you prepared for this one, if you want. And that one we are not going to spend many minutes on. But if you remember, I also showed you 2 weeks ago that we could, when we made the scatter plot between two things, something I know we've been doing also many years back in time. We could talk about the correlation between two things, and as part of defining a correlation coefficient, we could also talk about the covariability, the covariance between two things, the way two things vary together. 2 weeks ago, I gave you a formula for how to compute it based on some data, right? Here is a mathematical definition of the same thing, expressed not by integrals, which it could be, but here expressed by the e things. The e things are actually the same as integrals. But again, now we are getting out at the limit of what we can cope in this little course. But it's just to let you know, it can be also defined such a bivariate thing, which is a combination of two things. We can also theoretically define what we mean by the covariance between two things within a random system of two jointly modeled things. Whoa. That was the first part, the abstract part. So we jump to the next part.